And let's see. Hold on. Okay, it's set to like 75. I need it on my computer. Okay, I'm not doing that. Yeah, I'm not doing that.
No way.
I mean, that's what it says. You just came from the outside. Give it a minute. Give it a minute. All right. Lecture 12, our exam review. I know that this is a course in structural steel design, but I did ask before class how the concrete canoe placement went. Seemed to go well. Went faster than everybody's, which is always, that's good. So hopefully it's curing well. So, all right. Okay. You all have had me for class before, so I don't want to belabor this too long. I'm going to go through what's going to be on the exam. Open it up for questions that you may have for me. Okay. So, did everybody get the code? Everybody got it? Okay, logistics. You had me for class last semester for structural analysis. If so, you had my exams before. The format of this, the same. Okay, a series of conceptual questions, 2 or 3 computational problems. That's my exams. Again. The exam is not intended to be time critical, and the way that I address that is I use essentially a rule of 3. So if I can do a problem in 10 minutes, you should be able to do it in 30 minutes. And that's sort of my my metric. Regarding acceptable materials, for one, bring the manual. You need it. Just point blank. You can use a formula sheet. Put whatever you want on the formula sheet, except for fully worked out problems. We'll get to that here in a bit. Straight edge, maybe will help a little bit with some of the diagrams that you may generate. When it comes to the formula sheet, my big 2 rules is that just don't copy and paste example problems or material just totally straight from the slides. I mean, I don't mind if you include a table here and there, but my big thing is that it needs to be prepared by you. Put some effort into it. You can word process it, handwrite it. I don't care. Just use it a little. Put a little bit of time into it, because that effort of preparing the formula sheet, that is studying. Okay. And I'll collect those after the exam. I'll give them back to you, so don't worry. Sorry. Okay. What's the exam on? Everything that we've been talking about up through today, which is the fundamentals and tension members. So what am I talking about with the fundamentals? Be able to generally describe the process of structural engineering, be able to generally describe the difference between allowable stress design, LRFD, things like that. But the star of the show for this exam is tension members. So make sure that you can analyze tension members according to gross section yielding, net section fracture, block shear rupture, and slenderness limits. And make sure that you can design sections, either plates, roll sections, whatever, for prescribed loadings. And so when I say most economical, I mean lightest weight. Oh, I should go ahead and correct something. I moved this topic to a later portion in the class, so don't worry about that. Don't worry about the threaded rod thing. I used to do that on exam 1, but I've since moved it, so my apologies. Okay. Excuse me. All right. So regarding the rest of the slides, this is the key highlights for the last few lectures. So LRFD, generally what it means is that we are not applying a blanket factor of safety. We are instead individually factoring loads and resistances according to their uncertainties. For the loads, what we do is we apply statistically calibrated load combinations, right? So the way that it works is, instead of just factoring the loads, we have several load combinations which are intended to represent specific conditions of the structure. So for example, normal everyday use, earthquakes, high winds, etc. And we just consider the worst case scenario out of all of these, which is the one that produces the highest value that we would then use for design. Tension member limit states. We have gross section yielding, net section fracture, and then later on in this show we have block shear rupture. All right, let's talk about some tabs in the manual. So again, I suggest that you tab some pages out of section 1. What I suggest are the W's, the channels, the angles, and the WTs. Maybe a tab on the HSS, but other than that, I really don't think there's anything that you would need. For rolled shapes, I would tab this. This is table 2-4 where the FY and the FU values are available. Remember, whenever there's a range, we select the minimum value in that range because that's most conservative. For rolled shapes, use table 2-4. For plates, use table 2-5, although really, for most practical applications, the values are going to be the same, so not really a big deal. All right, the complete expression for net area is that the net area equals the gross area minus the area lost due to the presence of bolts plus any necessary stagger factors, okay? We get the area lost due to the presence of bolts by taking the bolt diameter, adding 1/8 of an inch, and then multiplying that times the thickness. What thickness? Well, whatever the bolt's going through. Our stagger factors are F squared T over 4G. G is the spacing perpendicular to the applied load. S is parallel to the applied load. That's for bolted connections. For most welded connections, net area equals the gross area. Shear lag factors. This is another one I would tab. This is on D3 or table D3.1 on 16.1-34. Whenever you're using this table, like the way I tend to suggest your thought process is the first thing that you should do is look at case 1 and case 2 and decide, are we in case 1 land or are we in case 2 land? If we're in case 1 land, I would say probably just ignore everything else. If you're in case 2, you definitely need to apply that, but then past that, look at cases 3 through 8 and see which ones apply. Our step-by-step process for design, and again, that's another one I missed, I'm sorry. I redid my slides this time and I had a boo-boo. Okay, so whenever we design a tension member, the first thing that we're going to do is determine the factored load that may be given to you, or you may be given service loads that you then need to factor, okay? After that, we compute our 2 design parameters, because those are going to guide what we look up. So we're going to compute a radius of gyration for design, that's L over 300. Watch your units on that. And then the gross area for design is going to be the load divided by the minimum of either this or this, okay? Now, whenever we select a section, and so based on constraints, what we're going to do is select the lightest shape that we can. But whenever we select that section, we usually do need to analyze it, simply because it's kind of hard to estimate U, and it's kind of hard to estimate the thickness in the design phase. Okay. When it's all said and done, compute your efficiency and summarize your results to ensure that that is in fact the lightest shape. Here's our block shear rupture capacity. UBS FUANT plus 0.6 times the minimum of this right here. You all just used this. I mean, probably like last night as you were getting ready for the homework, so I won't spend too much time on this. Just know that we're probably going to have UBS equal 1. Well, we are. I'll just say it. You're not going to have a situation where UBS doesn't equal 1 on the exam. Okay. And this, yeah, this was from a prior exam. We're not going to use threaded rods, so don't worry about threaded rods. Okay. Okay. Floor is yours. Q&A. Yes.
Are we going to have problems where we're choosing, like we have the design ones where we choose the member, but then are you also going to have ones where you're giving us the member and we're deciding if it's adequate?
Possibly, yes.
We're going to have both. Okay.
Possibly, yes. Okay. But what I would say is, okay, for an analysis problem, we should all arrive at the same answer regardless. For a design problem, it's got to be constrained to where we all arrive at the same answer. So, yeah, go ahead.
For the block shear, like the one on the homework.
Yes.
So there's the 4 corners. Whenever you do that, do you just do like all your calculations and then multiply that by 4 for the 4 different ones?
So since the homework was due today, and I'm not accepting late ones, I can pull up the solution. So, there are a couple of different ways to do it. I'll show you how I did it, and just bear with me. Okay. So, first off, all right, so yes, there's 4 individual blocks here, okay? I've got all of the associated properties here. What I did was this, is I computed the block shear capacity of a single block, okay? So I said, okay, here's the gross area and shear, net area and shear, gross area and tension, net area and tension for just this block right here, okay? So plug and chug and you get this for the capacity of a single block, okay? Now, I want to make sure we're all on the same page. This is the capacity for a single block, and this is a nominal capacity, okay? So to get the whole member, what I need to do is I need to multiply this by 4, since there's 4 of them, and I need to adjust by phi. So the actual answer was something like 450 kips. Now, what I was going to say was there's more than one way of doing it. Another way of doing it would be to multiply each of these areas by 4, and then just multiply this by 0.75. However works for you. This is how I like to do it. If you want to do it the other way, that's fine too.
Is it the same process of calculating block shear rupture if the member has like staggered bolts?
Let's get into, okay, that's a great question, okay? So the question was, what about for staggered? So I'm going to give you an answer, but I'm going to tell you, no block shear for staggered connections. I'm not going to make you do that. Okay? Right? All right. Now let me show you how you would, just to sort of make the point. Okay, so let's do this. Let's with me so far? Okay, so let's just say that that's the block. With me so far? Okay. This is how I would do it. So the question is, really the question is what's A and T, right? Because, I mean, this isn't going to be any different, right? The net area in shear is going to be the gross area in shear minus 1, 2, 3.5. But, hold on, the gross, if this is my failure block, whatever the gross area in shear and the net area in shear is, I have to double it because there's path up there too. Does everybody see that? Everybody okay with that? Okay. So the way I would do this is I would say this equals the gross area, right? Which the gross area, I'm just going to use that length, okay? And what I would do is I would say minus 2 bolt holes plus 2 stagger factors, where for this, just figure out what S is, figure out what G is. Now some of you might be thinking, well wait, isn't it 3 bolt holes? Well, there's 1 bolt hole here, a half, and a half. That's why it's 2. But again, I'm not making y'all do that, so don't worry about it. But that's, I mean, the point is, it's just another problem. So. That's how I would do it. How's everybody feeling about the exam? Anybody worried about the exam? Anybody concerned? Anybody stressed? Feel like they're going to yield under all this load? Should I just walk out now after that one? But yeah, no block shear for staggered bolt pass. Don't have to worry about that. Any particular homework that challenged you? Any particular assignment that was, I didn't get that? Everybody feeling chill? I mean, this is your time, but if y'all don't have any questions, we'll call it.
Let me look at my grades for the homeworks.
Okay. That's a good point.
See which one I struggled with.
Okay.
I think the ones with the structural analysis involved were most difficult for me.
You can do a structural analysis review.
Okay, let's talk. I'm not going to do a review of the entirety of CE 312, but we can look at a particular assignment if you want. You want to look at I think it was 2.4? Was that the one that, had the truss? I think it was 2.4.
2.5 is the one.
2.5.
Yeah, I think 2.5 was the one I did the worst.
Yeah, this is 2.5. Okay. Okay. So the first thing to do is, like, whenever you deal with this problem, just for one, factor the load, right? So both joints had the same load on it. So what I did is went through all three load combos, factored the load, okay? Now, this is Q, and everything's symmetric. So this vertical reaction right here, like if this is Q, I've got 2Q down, I've got to have 2Q up, so the vertical reactions here are Q apiece. Is everybody okay with that? That good? So past that, all I did was a method of joints problem. So for this one right here, like if I have Q up, I got to have Q down. And so this is what? Over 12, up 4. So if this is Q, that's got to be 3Q. And so if this is 3Q, that's 3Q. So that tells me the interior load based on this joint, the interior load is 3Q. Is that okay? Was that the part that was challenging on this one? Just been a while since you've done a method of joints problem. I can appreciate that. So what I can tell you is if there are any structural analysis requirements on this exam, they will be light. No ridiculous trusses. So I'll just leave it at that. But then once you do that, it's a problem like all others, right? Just analyze it, net area, shear lag factor, all that. The big thing on this one was that the shear lag factor was 1. It was just a plate, and it was all the cross-sectional components were connected. So that means that U is 1. This is what I meant when I said whenever you're assessing shear lag, first thing you ought to do is look at case 1 and case 2. Are we in case 1 land, or are we in case 2 land? We're in case 1, so U is 1, move on, okay? And then just, here's the load in the member, here's what it can withstand, everything's good to go.
We found 2 sets of LRFD equations in the slides.
You did?
Yeah. There was, me and Mike have it pulled up. For one of them, it says equation 2 was 1.2D, 1.6L plus 0.5 times LR or S or R.
That's an old one. That's the old one. The one that has 0.3 on the snow, that's the correct one.
Okay.
Here's what I'll do. I'll make sure that's correct on them. That just got updated recently, so I'll make sure they're all correct. But yeah, that just got updated somewhat recently. Yeah, they release ASCE 7 updates every so often. So they just one of the big reasons for that is that there was a study a couple years ago where they completely redid how the snow maps work. That's why that changed. So I'll fix that. Thank you for pointing that out, though, because I'm going to fix that, and then what's going on here? Yes.
Homework 2.2, failure path.
2.2.
Yeah. How to figure out how many failure paths?
Oh, yeah, this one, I mean, I'll say this. This one was a little challenging. I'll just level with you, okay? And, I mean, really what you have to do is just sort of test all of them. Like, what I'm getting at is, again, what are the rules? It has to leave all of the bolts intact, right? It's got to leave all the bolts intact, and it has to be along the lead line. So I guess my question is BEFJ, is that a potential path? What about BE? Well, here, let's just do a couple. Like, let's. Can I write on this? Never mind. I'll just do it here on the board. Let's just do this. So BEFJ. Is that one good? Okay. What about BEF HK? Is that good? Okay, what about BE HK? Is that good? No, it's not, because it would shear through that first bolt. Okay? So really what you got to do is just think of all potential scenarios where that would happen. And I mean, again, you can have some pretty interesting ones. So for example, like, let's see, C, D, E, F, H, K. Is that a potential option? Yeah. So when you start exploiting symmetry, yeah, I mean, you have quite a few that could apply. Okay. How do you identify them? Really, what I would do is just go through all potential permutations and see if they fit the rules. Okay. Now, let me say this. This connection, because of the way it was formatted, had, 11 different paths, right? I'm not going to do that on an exam. You don't have time. Yeah. That doesn't mean there aren't connections with more than one potential path, but I'm not going to do this. Does that make sense?
Okay.
So, again, the ones that you're going to deal with are going to have a much more manageable number of paths. So, like, for example, I'm just going to make one up. All right, first off, which side is the lead line? The stuff over here on the right or the stuff over here on the left? Left, right? So this bolt, this bolt, this bolt. First thing you need to do is identify the lead line. So on this problem, what I would say is every bolt, I would say every bolt is on the lead line but one. Is there one bolt that's not on the lead line? G. Bolt G is not on the lead line, right? No way it's on the lead line. But every other bolt is. That was one of the reasons why this one had so many different options. Okay? So, how many potential net area paths do you see on this connection I've drawn here on the board? I just made this up. How many do you see? 4? Well, let's identify them. Let's do, I don't know, give me a path.
A, B, C, D, E.
Okay. So this one, here, let me move this down here. So this is going to be the gross area minus how many bolt holes?
3.
Plus how many stagger factors? 2. Okay. How many other paths? What other paths are there? And what's this going to be?
2.
plus Noga stagger factors, right? That's it, right? Are there any more? So what I'm getting at is, this was pretty easy to identify, right?
Yeah.
There's only 2, right? That doesn't mean you don't need to be able to identify them, but I'm not going to give you a problem on the exam where you have to identify 12 of them. I'm not going to do that. So. That would be my answer to that question. Did I answer it?
Yeah.
Okay. But yeah, the specific like way to identify, number 1, on the lead line, and 2, leaves all bolts intact. That's the rule. So again, this path wouldn't work, right? Because think, if I take a pair of scissors and I cut through, let's say, paper plate, whatever, right? These 2 bolts are still holding it down. I'd have to shear through those bolts to separate the member. And my point is, I'm evaluating the strength of the member, not the strength of the member and the bolts. I'm going to look at the bolts later. Any other questions? Feeling comfortable? Going once? Going twice? Guess I'll, yep.
For the black shear for the C-plate.
The block shear for the channel?
Yeah.
Okay.
How it will be looks like when.
Well, so let me answer it this way. I don't have a be-all, end-all answer, but let me answer it this way. So I gave you an example right here where a common, so keep in mind that whenever we're discussing things in this class, what I want to do is spend most of our time talking about practical connection applications. Okay? So like, for example, could I come up with a problem where I have channels with bolts through the flanges?
Okay.
Yeah, I could come up with it, but is anybody going to do that in the real world? Not really. I mean, think about it. If I gave you a channel and I said bolt it to something, chances are you're going to bolt it through the web. That's what's going to happen, right? So what's the block going to look like? It's going to look like that. Okay? So how do we calculate? So let's just take this connection. Okay, let's just take this connection. All right? What's the gross area in tension? Well, it's going to be the length times whatever the thickness of the web is, right? Just going through the web. So gross area in tension is this length times the thickness of the web. Net area in tension is the gross area in tension minus the area lost due to the presence of bolts. How many bolts am I subtracting from the gross area in tension to get the net area in tension? How many? 2, right? 1, a half, and a half. With me so far? Now, let's talk about the gross area in shear. Somebody tell me how are they going to compute the gross area in shear? Let's say this length right here. Let's say this length is 10 inches. So if this is 10 inches, how are you going to calculate the gross area in shear? Anybody? That's not right. Times 2. Because there's a shear path here and a shear path here. So the gross, if this length is 10 inches, then the gross area in shear is 20 inches times the thickness. So the net area in shear is the gross area in shear minus how many bolts? 7. 1, 2, 3, 4, 5, 6, a half and a half, 7. What makes the channel challenging is the bookkeeping, not I mean, once you get the areas, the formula's the same. So what I'm getting at is you could have said, like for this problem, you could have said, okay, the gross area in shear is this length times 4 times the flange thickness. And then the net area in shear is the gross area minus 14 bolts, right? because you'd have 3.5 times 4. So you could have handled it that way. That would have been a perfectly valid estimate. I don't like doing that. I think what's easier is to just look one block at a time, but that's me. If you wanted to do it all at once, that's fine too. Just as long as we get the same PRN at the end of the day. Feeling good? Any questions? Yes.
One. So for angles, when we're looking for X bar, are you supposed
X bar, you said?
I was gonna ask, are we supposed to use Y bar instead when calculating it?
No. So I don't have let me give you a global answer, okay? Okay. I'm going to draw a really exaggerated angle, but you'll see what I'm doing. Is it clear from my picture, this is the long leg, this is the short leg? Okay, all right. I'm just saying, want to make sure it's clear. The centroid of this angle is about right there. What is X bar for shear lag? It is the distance from the connected face to the centroid. So the question is, which face is connected? If the bolts are going through this leg, okay, then the X bar connection is this distance. In the manual, that's X bar, okay? This dimension is Y bar, okay? Here's what I'm saying. I'm saying that it's not, if they're unequal leg, always use X or X bar, always use Y bar. It's where are the bolts going through, okay? But let me also add a dose of reality. If I had an angle like that, where are the bolts going to go through? The long leg, right? Which means, which value you're going to use? X bar, okay? By the way, look up an equal leg angle. What's the difference between X bar and Y bar if the legs are equal? They're the same, yeah. So that makes things a little nicer for you. By the way, which R value do you use for slenderness for an angle? R min, which for an angle is RZ, right? The Z-axis, right? Angles do not exhibit symmetry about the X or Y axis, which is why there is an RZ to begin with. Anytime there is a shape in the manual that doesn't exhibit symmetry with respect to either the X or the Y axis, there is a principal axis. Now, how do they figure out that principal axis? They break out a little thing called Moore's circle. Remember that? Moore's circle seems to be so mysterious. It's not that hard. What's that?
Probably isn't that hard.
It isn't. Okay. I'm going to explain Moore's circle in 30 seconds. Okay, you ready? All right. You cut a section like this. Cut it perpendicular. There's stresses inside, right? Okay. But what if instead of cutting a section like this, I cut it like that? The stresses are going to change, right? There's going to be some trig involved, right? I can relate these stresses to these stresses with a little bit of trig, right? I seem to remember in trigonometry that sines and cosines are really just coordinates on a circle. That's it. All Moore's circle is a transformation of stress as you take your cut and you do like that. Instead of cutting up and down, you cut it at an angle. What Moore's circle is trying to figure out is what's the worst way of cutting it to get the highest stresses, because that's how it's going to fail. That's Moore's circle, everybody. High level. I'm dead serious. That's all there is to it. Did that help? Is that how they describe it in mechanical land?
We didn't talk about Moore's circle because, quoting Dr. Chin, there are better ways to address the problems that it solves.
Eigenvalues, I know. It's all the same thing. It's all eigenvalue. Moore's circles, eigenvalues, all the same thing. I know what he's talking about. We could talk about eigenvalues in here if you want. That didn't, well, that was quick. That was, yeah, no. All right. Last chance. Going once, going twice. Everybody was going to be looking at you, man. We'll see you on Wednesday.